Okay, so welcome to Friday Happy Math Hour today. I am Melinda Camarillo. We are going over topics in Math 2412. Today we're looking at the binomial theorem, some counting techniques, and probability. These cover sections 9.5, 9.6, and 9.7 in your 2412 course. So you should be covering them around this time. Binomial theorem, some counting principles, and probabilities. Okay, so starting with binomial coefficients. Recall that a binomial is a polynomial that has two terms, bi for two. In this section, we're going to be looking at a formula that will provide a quick method of raising a binomial to a power, also known as expanding the binomial. So we have an example right here. X plus y is your binomial in parentheses to the power of n. And we can look at the value for several powers of n. If we start here, x plus y to the 0, anything to the 0 power is 1. That's how that one simplifies. Anything in the first power is just itself, so x plus y. X plus y squared, when we multiply that out, we get x squared plus 2xy plus y squared. X plus y to the third, you can see what we get there, to the fourth and to the fifth and so on. So we're going to be looking at these and the patterns and what we see. But let's observe a little more quickly what we see with the powers of x and y in the terms. So let's look at, for example, here, y to the x plus y to the third. You see we get x to the third. Going to the end, we get the y to the third. And in between, we have x squared y. Y is the power of 1. The powers will also add up to 3. 2 plus 1 is 3. X to the first plus y squared, 2 plus 1 is 3. So that has that property. The same with 4. Everything is to the fourth power, or it adds up to a power of 4. X to the 4, y to the 4. And all the other ones add up to 4. Power of x is 3, power of y is 1, so 3 and 1 is 4. Power of x is 2, power of y is 2, 2 and 2 is 4, and the same here, x is 1, y is 3, they add up to 4. So that is a commonality when you look at the powers of x and y. Again, now let's look at those more with the fifth power, right? X is 5, there is no y. We can write that as y to the 0, that would just be 1, that adds up to 5. Again, looking at the powers of x and y here, 4 and 1 is 5. 3 and 2 is 5, 2 and 3 is 5, 4 and 1 is 5, and 0 and 5. So again, the power that you raise the binomial to is going to be what all of these variable powers add up to, okay? So, and then we start with the x term that matches that binomial power. So right here, if you notice, we have x to the fifth, which matches that power, just that first one, the x. And then it goes down by 1, and then x to the 4, x to the 3, x to the 2, x to the 1, x to the 0, all the way down. We go the opposite way with the y, or the other term, whichever this would be. Right here, it's a y. So we start at the right, and y is to power of 5, then power 4, 3, 2, 1, and 0. Or you can start at 0, right, and go up by 1 for the y. So x, or the first term, will start with matching that same power, 5. And then y, or the next term, will start at 0, and they go down by 1. Or the y's would go up by 1, and the x's go down by 1, okay? So the power of y starts at 0 over here, and increases by 1 until you hit the same power of the binomial. And again, that's the opposite. X starts at 5, and you decrease by 1, okay? So that's the power, the pattern that we see with the powers. Let's look at the coefficients, or the numbers in front of all of these terms. Okay, the first one is a 1, then we have a 5, the number in front is a 10, the number in front here is a 10 as well. We have 5 right here, and then the last one, the coefficient, is a 1. So we're going to be looking at, where do these come from? Okay, where do we get these binomial coefficients, or the numbers in front of all these terms? For when the n is 4, the numbers in front are 1, 4, 6, 4, and 1. So there's a pattern there. Let's look at where we get those binomial coefficients. Okay, so it comes from the binomial theorem. Let n be a positive integer. R is going to be from 0 all the way up to n. When we have an expansion, x plus y to the n, what we're doing, These are all of the way we get the terms. You start with that first term, x to the power of n, and then x goes down by 1 power, and so on and so forth. Y will start up here with the power of n, and then go down as we go this way. Now, how do we get these coefficients? These coefficients, the numbers in front, come from this formula, NCR. We have the value of n is going to be n factorial, and I know we've talked about that before, how the factorial is, divided by n minus r factorial, so we subtract the n and the r, times the r factorial, so that's our formula for the coefficients there. You might also see this parentheses with n stacked on top of r, and that is the same as looking at it this way, CNR and CR right there. That's how we get our binomial coefficients. So let's look at that here, right? A plus b to the n. Whatever n is, that's our number on top. That's the n value. And we start with 0 on the bottom. R is 0. And then that number on top stays that n, but then we look at r becomes 1, r is 2, r is 3, and so forth, all the way to the very end. You get n with the same number n, okay? Another thing to notice here before we go on is look at the power of that second term. In this case, b matches that r value right here, right? The power of that second term matches that r on the bottom, okay? So let's practice using the formula with some of these. Find 25C4. So n is 25, r is 4. So here's the formula. I'm going to plug those numbers in. N is 25, 25 factorial all over. R is 4, 4 factorial. N minus r factorial, I do that first. So 25 over 4, 25 minus 4 is 21. So I get 25 factorial over 4 factorial times 21 factorial. A lot of times you can just do this in your calculator, plugging it in correctly. I've mentioned previously with the factorial, you should have the factorial buttons on your calculator. Again, it just looks like the exclamation point, right? You could also just kind of write it out to evaluate it. So 25 factorial is going to be 25 times 24 times 23 times 22. And we keep going all the way until we hit 1. So I wrote out the first few and then just times 21 factorial. On the bottom, 4 factorial is you multiply from 4 all the way down to 1, and then times the 21 factorial. So if we're going to simplify like this, we can see that the 21 factorials cancel. 4 factorial is 24, so that cancels, and you can just multiply the rest. So that's one way to simplify that. Okay, otherwise, as I mentioned, we can put this in our calculators. 25 factorial divided by the 4 factorial. I would do divide by parentheses, 4 factorial times 21 factorial at the bottom. Let's do another one. So we're going to use the same formula, but this is just presented differently. You see the parentheses and the 10 and the 3 stacked on top of each other. The 10, the number on top is our n, the number on bottom is our r. So I can still plug it in appropriately into the formula for n and r, okay? So it's n factorial over r factorial times n minus r factorial. 10 factorial on top. R is 3, so 3 factorial times 10 minus 3, which is 7 factorial. We can simplify this. The 7 factorial part of 10 divided by 7 factorial cancels out, and just multiply to get the rest, and we get the value of 120. So this is a formula we use, notice, to help us find all these coefficients. When I have a number n and the number r, I can plug those numbers into the formula here to help us get these coefficients of our binomials or our expansions. Okay, we can also use Pascal's triangle. Pascal was a mathematician. We use a lot of the work that he came up with. So we have the Pascal's triangle. How it's constructed, well, you start with a 1, and then you can write all ones along the end, right? You put your second row of 1 and 1. And the way you get all the numbers is by, you just add the 2 numbers on top of it to get you that number, right? So 1 and 1 is 2. 1 and 2 right here is 3. And you can see some of these pointed out. 4 and 6 is 10. Right here, 4 and 1 is 5. right here 15, and 6 is 21. So again, if we start with, we know we have ones all along the outside. We start with a 1 and a 1 and a 1. You're just adding the two numbers on top to get that number on bottom. Okay, so pretty cool. We can continue this on with that pattern. And that helps us, that correlates to the coefficients of our binomial terms. It works out that way. So for example, here's the expansion of some of these binomials to different powers, 0, 1, 2, 3. Notice the coefficients. They match with the row of the Pascal's triangle. So let's go right here to x plus y to the third. Okay, look at the coefficients. I have a 1, a 3, a 3, a 1. So if I go to the third row, so we start with the 0th row. So this is 0, 1, 2. Here's my third row. Look at those numbers match. It's a 1, 3, 3, 1. Just like I showed you right here, coefficients are 1, 3, 3, 1. So if you know Pascal's triangle, or you can generate Pascal's triangle, the row of the triangle will correspond to the coefficients of the binomial to that given power, right? Let's do one more, like the fifth row of Pascal's triangle would match with x plus y to the fifth power. So look at these coefficients, 1, 5, 10, 10, 5, 1. So go to the fifth row of Pascal's triangle, and what do you notice? 1, 5, 10, 10, 5, 1. So we can use these numbers, which are going to be generated right here. So instead of using the formula, we can use the numbers. So that's just an option, an idea for those of you that want to go ahead and use that Pascal's triangle. Okay, so let's do another example. Let's write the expansion. So we want to take x plus 2 to the fourth power. First term is x, second term is 2. The previous examples, it's been x and y, or a and b. Now we have an x and a 2. Power is 4, n is 4. Okay, so here's the formula using the formula. Okay, here's the Pascal's triangle if you want to see that, and we'll see how it matches. Power is 4, so we would use the fourth row right here. But we can also use the formula and plug everything in. So let me show you how that works. So plugging everything into the formula, our n is the power. So n is 4. So I start plugging in a 4. And we start with r0. And then my next term is 4, r1, 4, 2, 4, 3, all the way till we hit the n and r match 4, 4. Okay, now what do we do with the powers? Remember that first term is an x. We start with the power of 4. And we go down. So x to the 4, x to the 3, x to the 2, x to the 1, x to the 0. That second term here is a 2. So if I start on the right, I start with 2 to that fourth power, then 2 to the third, 2 to the second, 2 to the first, 2 to the 0 power. Or if you start with the first term and want to write it out, the second number, the 2, will start with power of 0 and on up, okay? So if we calculate these 4 and 0, I get 1. Using the formula, 4, 1 would be 4. 4, 2 would be 6. 4, 3 would be 4. And 4, 4 would be 1. So we can use the formula, or notice that these are going to be the same values of the triangle. So 4, 0 is 1. 4 right here, 6, 4, 1. The coefficients match. So that's one way we can find those coefficients. Again, we have it set up so we can plug the n and the r into the formula, or we can just match. Power is 4, go to the fourth power of the Pascal's triangle and take those coefficients. Okay. So now I'm going to plug everything in and evaluate appropriately. So I have a 1 right there, x to the fourth, 2 to the 0 is 1, 4, 1 is 4, x to the third, 2 to the first is 2, 4, 2 gives me 6, x squared, and 2 squared is 4. So I'm evaluating. I plugged everything into the formula, but then remember, you got to evaluate everything in each term, right? 4, 3 is 4. Whether we use the formula or the triangle, we get a 4. We have an x, and then we have 2 to the third, which is 8. Lastly, 4, 4 is 1. X to the 0 is 1, and 2 to the 4 is 16. So I wrote out what everything is, and now I need to multiply everything to get all my specific terms. So the first one, I have 1 times x to the 4th times 1, 1x to the 4th. Right here, I multiply 4 and 2 with x to the 3rd, 8x to the 3rd. Right here, 6 and 4 is 24 with x squared. 4 and 8 is 32x. And then lastly, 1 times 16 is 16. So I plugged everything into the formula. evaluated everything so that I was able to get each of my terms simplified, and that would be the expansion there. X plus 2 to the fourth gives you x to the fourth plus 8x to the third plus 24x squared plus 32x plus 16. Okay, let's do another one. This is 2x minus y to the fifth power. So I'm just going to take those values from the Pascal's triangle. Those are going to be my coefficients. And again, if I plugged them into the formula, that's how it would look. And so here's my expansion. So 5, 0, or 1, take that coefficient. Okay, we see how we set up the coefficients. Now my first term is 2 times x. So then I write 2 times x, 2x, and I start with power of 5, right? 2x to the fifth. On the next term, it's 2x to the fourth, 2x to the third, 2x squared, 2x to the first, 2x to the 0. The next term here it's minus y, so you have to put a negative y. Okay, all the other ones have been plus. This is a minus, so I do minus y. I start here with 0, so now this is minus y to the 0, minus y to the first, minus y to the second, minus y to the third, minus y to the fourth, all the way till we get to minus y to the fifth. Now, one way we can double check that we did it correctly, look at these powers. They all have to match. They have to add up to n. So n is 5, so 5 and 0 is 5. Look at my powers. 4 and 1, 5. 3 and 2 is 5. 2 and 3, 1 and 4. So that's another way to check that I did the powers correctly. So now I just have to evaluate, find the value for every term. Okay. So again, I can use my formula to evaluate each of these, but they should match Pascal's triangle. So I'll replace that. So 5, 0 is 1. 2x to the fifth, 2 to the fifth is 32, and then x to the fifth is x to the fifth. Negative y to 0 is 1. Here, 5 and 1 is 5. 2 to the fourth is 16. X to the fourth is also x to the fourth. Negative y to the first is negative y. Evaluating here, 5, 2 is 10. 2x to the third is 8x to the third. Negative y squared, negative times negative is positive. 5, 3 is 10. 2x squared, 2 squared is 4 times x squared. Negative to the third, negative 1 to the third is still a negative. Negative y to the third. 5, 4 is 5. 2 to the x to the first is 2x. Negative y, or the negative 1 in front to the fourth, becomes positive. And then you have y to the fourth. And over here we have 1. 2x to the 0 is 1, and a negative 1 to the fifth stays negative. So that's the next step. I evaluate each term. And now I keep going, multiply everything. This is just 1 times 32, so 32x to the fifth. Here I have a negative 1 times 5 times 16 is negative 80, x to the fourth. Here, 10 times 8 times 1 is 80, x, I just notice that one. The variables might have switched, but be careful with that one. Or am I? Sorry, guys, I'm ahead. I clicked too much. So 10 times 8 is this one, 80 x to the third y squared. Negative 40 comes from the 10 times the 4 times the negative 1. So that's negative 40 x squared y to the third. And then this one, 5 times 2 is 10 x y to the fourth. And the last one, 1 times negative 1 is negative y to the fifth. That's how all of those get simplified. And then that would be the final answer right here for that expansion. Okay, so pretty cool. So again, using Pascal's triangle, we have all the coefficients. And then whatever that n is, you can use a formula or not. But we use that n to get the power of all of these terms, right? Starting with the first term, 2x, take that to the power of 5 and on. The second term here was negative y. We start with the power of 0 and on, and then you're simplifying every term to get that expansion. Okay. Another example, this is y minus 3 to the third power. So let's fill all of this one in. So we start with y, the first term, to the third power. Then y to the second power is the next term, y to the first power, and then y to the 0. Okay. Our next term is negative 3, so we start with negative 3 to the 0, negative 3 to the 1 for the next term, negative 3 squared, and negative 3 to the third. That's the setup there. So now we just need the coefficients. We can use Pascal's triangle, or we can use the formula. N is 3, so we start 3, 0, 3, 1, 3, 2, 3, 3. So if you want to use the formula that we had before, you can, or write out Pascal's triangle and get these values from that third row. Simplifying 3 zeros is 1. Y to the third is y to the third. Anything to the 0 power is 1. That's my first term. 3 1 is 3. Y squared is y squared. Negative 3 to the first is negative 3. 3 2 is 3. Y to the first, negative 3 squared is 9. And then over here I have 1. Y to the 0 is also 1. And negative 3 to the third is negative 27. Simplifying each term, this is y to the third. 3 and negative 3 is negative 9y squared. 3 and 9 is 27 with y. And then multiplying all of these, 1 times negative 27 is negative 27. So that is our final answer for the expansion. Okay. Okay, now this one just wants us to find the fourth term. We don't need to expand it. We don't need to take this to the 7th power and do all of those terms. We just need the fourth term. So here's our formula again. This is the first term. Here's our second term, third term, and so on and so forth. I'm only wanting this fourth term. So let's look at some of the patterns, right? We notice when you have the N, the R in front, the R is 1 less than the term. So for the second term, for example, R is 1 less, which is 1. For the third term, R is 2. The fourth term, R is 3. So that's what I'm going to plug in to help me find that coefficient. And what is the N? The N is always the power of the original one, in this case, 7. Okay, so for the fourth term, I will use in the formula 7 with 3, again 7 because that's the N, and again the R on the bottom is 1 less than the term. I want the fourth term, so the R is 3. Okay, 3x plus 2y to the 7th. The 3x is the first term of the binomial, 2y is the second term, or the B, right? So I have 3x, 2y. I know I'm going to use 7, 3. Now, the R matches the power of that second term of the binomial, okay? So again, I have 7, 3. I'm going to use that to find the value of that coefficient in the formula. I know my terms of the binomial are 3x and 2y, so I'm going to have 3x to a power and 2y to a power. The power of the second term matches that R right there, so that's 3. Now remember, the last thing that's going to help us figure this one out is the powers have to add up to the N. So N is 7. So if this power is 3, then this power has to be a 4 because they have to add up to that N number. Okay, so that's how we're going to set up when you just want a specific term. So this would be just the 7th term. I don't need to find all the other terms. I don't need to expand. I just need to get this term. So now I can evaluate this term. Again, you can use the formula. 7C 3 with NCR, right? Plug in the N and the R, so we get 35. 3x to the fourth is 81x to the fourth, and 2y to the third is going to be 8y to the third, right? Because 2 to the third is 8, and then y to the third is y to the third. So now I need to multiply all these numbers, okay, that I got from simplifying. That gives me 22,680, x to the fourth, y to the third, okay? Let's do another one. Find the 8th term of the expansion. Again, here's my formula, but I need to figure out which one of these I have for just the 8th term, what numbers I plug in just to find the 8th term. Okay, so remember, R is 1 less than the term that I want. N is always the power of the binomial. So in my case, N is going to be the 9. And I want the 8th term, so R is going to end up being 7. Okay, for the 8th term. So 9 is my N. R is 1 less than the term I want. R is 7. So I have that. Okay, 1 less than the term that I want. Okay, here are my terms for this one, 6x and 2y. Okay, so I know that N is 9, R is 7. Remember, that second term of the binomial has that same power of R, so 2y is to the 7th power. Now these two have to add up. Powers have to add up to the 9. So if this is 7, this must be a 2 because 7 plus 2 is 9. So this is what I need to evaluate right here. This is going to give me the 8th term. 9, 7, you can use a formula. That's 36. 6x squared, well, 6 squared is 36 times the x squared. 2y, 2 to the 7th is going to be 128, y to the 7th. Now multiply all the numbers, all the coefficients there. 165,888 with x squared, y to the 7th. Pretty cool. Okay, so now we're going to move on to some of the counting principles we have. Okay, so let's look at this one, selecting pairs of numbers at random. Example, you place 8 pieces of paper numbered from 1 to 8 in a box. You draw one piece of paper at random from the box and record its number, and then replace the paper back in the box. Then you draw a second piece of paper at random from the box and record its number. Finally, you add the two numbers. So how many different ways can you obtain a sum of 12? So we're going to count the different ways to obtain a sum of 12 using two numbers from 1 to 8. The first number, we're going to go from 4 to 8 only because numbers below it, so for example 3, you're not going to get the sum of 12 because 3 the highest it can be added to is a number of 8, and 8 and 3 is 11, so that's not going to work. So 3 and numbers less than that are not going to be able to add up to 12. They're too small. Okay, so we're only using from 4 to 8. Okay, so we put what the second number must be to get a sum of 12. So 8 with 4, 7 and 5, and so on. So these are the 5 different ways we can get a sum of 12 because you're just listing out the numbers and finding the matches. And we know that by writing them out, there's only 5 ways we can do that. So that's an example here of the counting principle. So counting principle is basically going to tell us like how many ways there are of getting something or having something occur, right? So let's look at the fundamental counting principle. Let E1 and E2 be 2 different events. The first event, E1, can occur in M number of ways. After E1 has occurred, E2 can occur in M2 number of ways. The number of ways the 2 events can occur is by multiplying the M1 and M2. So multiplying the number of ways the first one can occur times the number of ways the second one can occur. So let's do an example. How many different pairs of letters from the English alphabet are possible? Pair. Pair is 2. Okay. How many ways can we pick then 2 letters from the English alphabet? Well, we're going to set that up by first looking at all our possibilities. And there's 2 numbers. It's a pair. So how many ways can I pick the first number? Like I said, there are 2 events. The first event is the choice of the first letter, and the second event is the choice of the second letter. The English alphabet contains 26 letters, so there are 26 ways that I can choose each letter, right? So how many ways can I pick a letter from the English alphabet? If I have all the letters in the alphabet, I'm going to randomly pick one. There's 26 possibilities. And then how many ways can I pick the next letter? Also 26 possibilities. So the counting principle tells us that when we have certain events, how many ways are there of getting an outcome? Well, you multiply the number of possibilities for each time, right? So I have 26 letters for the first choice, 26 letters for the second choice. You multiply these, and that is how many ways you can pick 2 letters from the English alphabet. So if I pick 2 letters from the alphabet, I have 676 ways that I can do this. Okay. This reminds me, just a quick outside note. If you guys ever go to a fast food place, sometimes, I don't know if it's Sonic or Whataburger or whatever, I've seen a sign that's like, you have 1,000 different ways of ordering a burger, for example, or at Sonic, maybe you have 2,000 ways of ordering a shake. So they're probably multiplying all the different ways you can order. Maybe you can change the bun or your toppings or whatever. So that's a cool example of the counting principle, right? How many ways there are of getting something. And those are just some examples there. Okay, but going back to more examples from your book. This is coming from number 30. For many years, the state of California used 3 letters followed by 3 digits on its automobile license plates. Okay, so how many different license plates are possible with this arrangement? Okay, so again, remember, there's 26 letters in our alphabet, and for digits, there's 10. So if you think 1 through 9 plus 0, so that's 10 digits. Okay, so again, the counting principle, we're going to multiply all the possible ways there are of obtaining each part of the license plate, okay? This one says we're going to have 3 letters. So the first 3 are letters, and then the next 3 are going to be digits. So how many letters are there? There's 26. So I have 26 ways of choosing that first spot in the license plate, another 26 ways for the next one, and another 26 ways because they're all letters. How many digits? I have 10 digits to choose from, and I have 3 different digits, so I have 10 times 10 times 10. So how many ways or how many different license plates are possible? You multiply all of that. 17,576,000 when you multiply. Okay, well, the state ran out of new numbers, so the order was reversed. 3 digits followed by 3 letters. How many license plate numbers are possible this time? Well, it's still 6. However, the first 3 are digits and the last 3 are letters. They're going to be different arrangements, but it's actually the same. I have 10 options for my digits to choose from. I have 26 letters to choose from. When I multiply all of this, I actually get the same. So the arrangement is different, but the number of license plates I can make is the same. What if all those numbers were used up? Then we're going to do license plates with 1 letter, then 3 digits, and then 3 letters. So then how many new license plates are possible with this new arrangement? So now there's going to be 7 spots on the license plate. It says the first one is going to be a letter. Then you have 3 digits, and then the next 3 are letters. So again, how many license plates are possible? Well, we just multiply all the possibilities of every single slot, right? So the first one's a letter. I have 26 options. The next ones are digits. I have 10 options for each of those. And then I have 26 options for the last 3, all the letters. When I multiply all of this, 456,976,000. So that's just how many possibilities there are based on how many possibilities for each slot that you're picking, right? Okay, so similar goes along with the counting principle is permutations. Okay, so an application of the fundamental counting principle is in determining the number of ways that n elements can be arranged in order. An ordering of n elements is called a permutation. So let's do a few examples here. A baseball coach is creating a 7-player batting order by selecting from a team of 15 players. How many different batting orders are possible? So you're going to recognize, I'll show you some specifics right now, but a permutation is when you're picking from the same group, right? In the previous example, we were picking letters of the alphabet and then we were picking digits, right? Numbers. It wasn't from the same group, but this is. So you have 15 players. I'm not picking a player and a color, right? I'm picking from the same group of players. So once I pick a player, he's not part of the pool anymore. He's not part of the options anymore. That's a permutation. And we're going to see that with combinations as well. So it's when you're picking from the same set of things that it's either a permutation or a combination. And with a permutation, the order matters, right? So here's the example. We have 15 players on a baseball team and you want a batting order. So those of you that are baseball fans, you know the order in which the players go up to bat matters, right? Depending on what base they're going to get to. And then you want to bring someone at the end who can kind of hit a home run and bring them all in, right? You don't want your first player to hit a home run and then you lose out and maybe bringing all the other players in. So the order is important here. Okay, but let's just use our counting principle to see how we would do this. Okay, he has 15 players and he wants to choose 7. So there's 7 slots here because we're choosing 7 players, right? Well, all 15 players are there. How many ways can he choose the first time? He has 15 players to choose from, right? But once he chooses one of those players, he only has 14 players left. Okay, so then he chooses the first 2. He had 15, now he's going to have only 13 left, and so on and so on. As you keep choosing, you're 1 down, right? The idea is the same, fundamental counting principle. We're multiplying the number of ways you can choose each player. The reason, again, it goes down by 1 is because it's from that same group. And once you pick one from that group, you have less to pick from, okay? But same idea, you can multiply all of this and get the number of ways you can have the 7-player batting order, okay? Let's do another example. You want to pick 5 children to pose for a photograph. So how many ways can 5 children posing for a photograph line up? The idea is the same. Here are the 5 slots for the 5 children. If you want them in a line, that means order, right? And if it's a photo, the order matters, right? You maybe want the tallest to the smallest. I don't know. It's going to look different if it's arranged differently. So we can pick 5 children the first time. Again, but once we have that child lined up, we only have 4 to pick from the next time. Then 3, then 2, then 1. Multiply, we get 120. Okay, so this will work with permutations. If you recognize it's a permutation, you're picking from the same group and order matters. You can multiply and get the answer. However, there is a formula, so we can look at that, and that might give us a shortcut here. So permutations of n elements taken r at a time, and PR. So n factorial over n minus r factorial is the formula we can use for these. Okay, n is going to be the number of people or things in our group. R is going to be how many you're picking from. Okay, so doing these again, just showing you the formula. Look at this first one over here. N was 15 because I'm picking from 15 players. Well, how many was I picking? 7. So I plug in the 15 for n and 7 for r. So 15 factorial, it does start like 15 factorial, but I stop at a certain point because I'm only choosing 7 of them. So I end up dividing by 8 factorial, 8 and on, right? So plugging into the formula, I get the same thing as I multiplied over here. And it gives me the same thing when I do 15 factorial divided by 8 factorial. So to show you guys how to do the other one, it was the same. There's 5 people that are going to be in this photograph. I'm choosing 5. 5 choose 5. Plug it in. Okay, 5 factorial over 0 factorial. 0 factorial is 1, so this ends up being 5 factorial. And you do see we did 5 factorial, 5, and we multiplied every number on down up to 120. So that's just the formula showing you that we can do it that way. Okay, what is a combination? So in counting the number of permutations of a set of elements, the order is important. That's what we just did, permutations. There's another method of selecting subsets of a larger set in which the order is not important. Subsets, such subsets are called combinations of n elements taken r at a time. So a combination is the same as a permutation in the sense that you're picking from that same group. However, the order doesn't matter. So if we're just picking 15 players from a team to just take a trip or something, they don't need to be in an order like the batting order. That would be an example of a combination. Okay, so let's look at some of these right here. And how many different ways can 3 letters be chosen from these letters A, B, C, D, and E? Again, the order is not important. Okay, the subsets represent the different combinations of 3 letters that can be chosen. This is the answer here. How many ways can we choose 3 letters from all of these? Here they are. Okay. When order is not important, we end up with 10 different ways these letters can be chosen from 5 letters, A, B, C, A, B, E. You can see all of them. The order doesn't matter. Okay, so there's 10. So the set ABC for a combination would be the same as CBA if I move the letters around. Okay, so for combination, all of those don't matter. So here's the difference. If this was a permutation, okay, all of these are different outcomes because the order would matter. So if I just look at these 3 letters, A, B, C, and I just rearrange them, I could get ACB, BAC, BCA, CAB. Because all of these matter, order matters, these would be a permutation. But with a combination, what I'm doing is I'm cutting out all these extras. So all of these end up being just one outcome for a combination, okay? Because the order does not matter. So there's a formula we can use here, and it's NCR. If you notice, this formula is the same that we use to find the coefficients in our binomial expansion. So we're applying it in a different way, but guess what? It's the same formula. So one less formula for you to have to remember. Okay, so we're going to use this formula to do some of the examples. And before I forget, actually, if you kind of look at it, the first part of the formula is our permutation formula. The n factorial over n minus r factorial, that's our permutation formula. You're just dividing by an extra r factorial, which helps get rid of all those repeats. right, that we saw previously that don't count here for the combinations. Okay, so here's an example. And how many different ways can a jury of 12 people be randomly selected from a group of 40? That's important. Randomly selected, order doesn't matter. So we're going to pick 12 people from a group of 40. Again, combinations and permutations, we're picking from the same group. Okay, that's how we know. Okay, so 40 choose 12. So 40 is our N. That's how many we have in the big group. And how many are we choosing? 12. That's our R. So plugging this in appropriately, 40 factorial over 40 minus 12 factorial times the R factorial, which is 12 factorial. 40 factorial over 40 minus 12 is 28 times 12. We get this number right here. Okay, that's a lot. There's lots of ways we can pick 12 people. Okay, so let's do this one. An employer interviews 12 people for 4 openings at a company. 5 of the 12 people are already employees. They're current employees. All 12 of these applicants are qualified. In how many ways can the employer fill the 4 positions when A, the selection is random, okay, and B, you want exactly 2 selections that are current employees? Let's focus on A first. The selection is random, so it doesn't matter if they're current employees or not. Okay, 12. So from the pool of 12 people, I want 4. And that's why it is 12 combination 4. So how many are we picking from? 12. And how many are we picking? 4. So we have the formula there, plugging it in appropriately. We end up with 12 factorial over 8 factorial times 4 factorial, which is 495. So that would be A. But let's look at B. So it says exactly 2 selections are current employees. So we need to know, well, how many ways can I pick those employees from the current employees pool? And then, well, how many ways do I pick the other ones, right? If 2 of them have to be current employees and I want 4, well, then the other 2 can be any of the other applicants. Okay, well, how many ways to pick the current employees? Well, again, how many current employees are there? Again, we're picking from how many are we picking from versus how many are we picking? 5 are current employees. So if I want the first 2 to be current employees, I only have these 5 to pick from. 5 choose 2. That's that one. And how many ways can I pick everybody else? The other 2? Well, I'm picking 2. I have 12 total, but if 5 are current employees, so 12 minus 5 is 7. So then how many ways can I pick the next applicants? It's 7, choose 2. So if I do 5 choose 2, I end up with 10, plugging all of that into the formula, and then 7, choose 2, plugging that into my combination formula appropriately, I get 21. Now, just like our counting principle, you multiply. Well, how many ways are there of picking the current employees times how many ways there are of picking the other 2? So then I multiply these 2 here. 10 times 21 is 210, okay? Another example. A standard poker hand consists of 5 cards dealt from a deck of 52. So those of you who are not familiar with all of the cards in a deck of cards, we have them here. There's 52. You can look at, all of them go from ace and then 2, all the numbers 10, jack, queen, king. We have suits, we have hearts, we have diamonds, we have clubs, and we have spades. So you can see this all right here, right? So we're picking 5 cards. 5 cards from the 52. So how many different poker hands are possible? Order is not important. Anybody knows if you play poker, when they pass you your 5 cards, it doesn't matter the order they give them to you in. You can rearrange this. So this is an example of a combination because from the 52, I want to take 5. Okay. Combinations, 52, choose 5. I plug it in appropriately into the formula. 52 factorial all over 52 minus 5, which is 47 factorial times 5 factorial. Again, you can choose to plug that into your calculator appropriately. We can simplify it if we want first, but in the end, we are getting 2,598,960 different poker hands that are possible. So different ways that you can get 5 cards out of the 52. Okay, so now we're going to move on to probability, and these counting techniques are going to help. Okay, so any happening for which the result is uncertain is called an experiment. The possible results of the experiment are outcomes. The set of all possible outcomes from that experiment is the sample space. And any subcollection of a sample space is an event. If an event, E, has n of E, or equally likely outcomes, and its sample space S has n of S, or number of S, equally likely outcomes, then the probability of the event is P of E, or probability of E, equals the number in E over the number in S. So to quickly just summarize that, the probability of something is the total number of possibilities. That's N of S, is our sample space. Well, how many total possibilities are there? But on top is just, well, how many of those are the favorable ones, or the ones in our event that we want to happen, right? So it's the part over the whole. So you take the part, the favorable event that you want, out of total possibilities. And that is your probability. Okay. So a probability, when you get an answer here, it should be a number between 0 and 1. You can include 0, you can include 1. So the probability should be between 0 and 1 inclusive, including 0 and 1. So anything outside of this, you know you did something wrong. No negatives, nothing greater than 1 should not be the answer for a probability problem. Okay, right here, probability. Probability is 0, that means it's impossible, cannot happen. At the other end, if the probability of something is 1, that means it's for sure going to happen. And then anything in between is also a probability. So the closer you get to 1 is the more likely something's going to happen. Something right in the middle, probability of 0.5 or 1/2 or 50%. The event is just as likely to happen as it is to not happen, right? So your 50-50 chance in the middle, okay? So let's do some examples of finding probability. 2 coins are tossed. What is the probability that both land heads up? Well, first we need to find the total number of possible outcomes so we can use our counting principle. So we're going to toss 2 coins. There's 2 ways, 2 outcomes for the first coin, right? We can get the first coin to land heads or tails up, right? Well, and then we do a second coin, and it's the same thing. It can land heads or tails, right? So we multiply, so then there's 4 possible outcomes for tossing a coin 2 times. How many outcomes the first time? 2. How many outcomes for that second coin? 2. So we have 4 outcomes, and here I'm going to list them, right? We can have heads with heads, a heads first and then tails first and then heads, or tails on both tails and tails, right? So this is considered a sample space. This is all possible outcomes. What is our outcome, right? What is the probability that both are heads up? That's our favorable outcome right here. So again, the outcome we want, the event we want, is the 2 heads. S is all possible outcomes. So remember, probability is the number in our outcome, our favorable outcome, our event, all over total possible outcomes, right? Well, how many in our event? How many of the outcomes we want? The 2 heads, 1. Out of how many total outcomes are possible? 4. So the number in E all over the number in S, 1 over 4 for the probability of getting that outcome for tossing the 2 coins. Okay, you're going to see probability a lot with a deck of cards as well. So here it is again, so you guys can see it. 1 card is drawn at random from the deck of 52 cards. What is the probability that it is an ace? Okay, so the deck has 4 aces. So remember, going back to probability, it's the number in our event, the number of outcomes that we want, over the total number of outcomes, right? So let's look at this one. We want an ace, right? So that's our number in E. That's the event that we want, right? So we have 4 aces, right? However, we divide that by the total number of cards. There's 52 cards, right? So again, number in E, number of our outcomes that we want is an ace. So there's 4. How many total possibilities are there? How many total cards are there? 52. So the probability here comes from 4 out of 52, always reduce. So that reduces to 1 out of 13. So the probability here is 1 out of 13 for drawing an ace. Okay, here's another example of probability. We have this chart here. It says the Human Resources Department of a company has compiled data showing the number of years of service for each employee. The table shows the results. What is the probability that an employee chosen at random has 4 or fewer years of service? And then we're going to look at what is the probability that an employee chosen at random has 9 or fewer years of service. Okay, well, it's always part over whole. We want the part in our favorable event out of the total number of possibilities here, right? So we're going to start by finding the total number of employees. That comes from all of these right here, right? They're kind of separated out, but our total number of all of these would be all of these added up. So that's our first step. We're going to add all of that up. We get 529. So now let's look at each one, A and B, okay? What is the probability that an employee chosen at random has 4 or fewer years of service? Right here. Employees that have 0 to 4 or fewer years of service, here we are, 157. Okay, so we already found previously that the total number of employees was 529. So if A is our event, the favorable event of choosing an employee with 0 to 4 years of service, so our probability then for that event is this number, 157, out of the total number of employees, 529. So we can leave this as a fraction. Careful how they want the answers. The previous ones we've left as a fraction, we just reduce. Sometimes they might want the decimal version, so you would just divide these. So the probability is 157 or 529, or divided out, the probability is 0.297. Okay, either will work. So part B, what is the probability that an employee chosen at random has 9 or fewer years of service? Again, we know that the total is 529. So now we're looking at how many match the criteria or our favorable outcome, right? So we already did 0 to 4, that's 157. Let B be the next event, which is the employees with 5 to 9. In total, I want all of the employees that have been there 9 or fewer years. So that includes the 0 to 4 as well as the 5 to 9. So I can take these two events. I know previously it was 157 out of 529, but now I'm also including this number right here, 89 out of 529. So these two events don't have any outcomes in common. The way we do this is we add them up. So the probability of A, which we had before, which was 157 out of 529, plus the probability of B. So together, I add those up. I get 246 out of the 529. And again, writing that as a decimal is 0.465. Okay, so more examples of probability. Find the probability for the experiment of rolling a 6-sided die. A lot of common examples you see with probability involve decks of cards or die or coin tossing. Those are some of the examples you should be familiar with, okay? Remember, the formula is the same. We want the number in our event over the total number possible. So this will be good to know when you're going to roll a 2 die or a 6-sided die twice, or just say roll a die twice. These are all your outcomes. Let's say the first die are white, the second die are red, and you can see all your outcomes, right? So you could roll a 1 and a 1. You could roll a 1 with a 2. Looking at all of the possibilities, this one is a 2 with a 1, a 3 with 1, and so on and so forth. Okay, so we can look at it that way. Sometimes I've seen these written like ordered pairs, right? 6, 6, 6, 5, or here I just like the picture with all the die. Okay, now they want the probability of the sum is 6, the sum is less than 11, or the sum is odd and no more than 7. So all of these involve the sum of the die. So I went ahead and found a table that has all the sum, right? These, I get a 1 and a 1, but you add, that's 2. A 1 and a 2, you add, that's 3. A 1 and a 3, you add, that's 4. So here is the sum, right? 1 and 1 is 2, 2 and 2 is 4. So this is going to help us to find some of these, right? For the first one, the sum is 6. Okay, so our probability comes from, well, what is the number in that matches this event? how many outcomes have a sum of 6 over the total number of outcomes, right? Well, here we go. All of these are a sum of 6. So that's 1, 2, 3, 4, 5 favorable outcomes, 5 outcomes that meet the criteria of a sum of 6. And there's 36 possible outcomes. So there's 6 ways to roll the first die times 6 ways to roll the second. So there's 36 possible outcomes. So again, looking at these favorable outcomes when the sum is 6, that's going to be 5 out of 36. Okay, what about when the sum is less than 11? So let's look at those favorable outcomes. Well, when I look here at all the sums, they all look like they're less than 11, except these last three, 11, 11, and 12. So it's actually going to help me to do the opposite. I'm going to like not count those. So there's 36 outcomes. There's only 3 that aren't favorable. So if I do 36 minus 3, that means there's 33 of these outcomes that have a sum that's less than 11. Out of 36 total outcomes, always reduce. That reduces. If I divide by 3 on both top and bottom, I get 11 out of 12. What about the last one? The sum is odd and no more than 7. So how many of these outcomes have an odd sum that's not more than 7, so it's less than or equal to 7? So here are my outcomes. These have a sum of 7, odd, sum of 5, and the other odd is 3. So what happens when I add all these up? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 12 outcomes that meet this criteria that are odd and less than or equal to 7. Out of 36 total outcomes, reduces to 1/3. So for probability, again, part over whole, the favorable part or the number of outcomes that match your criteria out of total number of possible outcomes you can get from that, okay? Okay, a few more examples. 2 events are independent when the occurrence of one has no effect on the occurrence of the other. So if A and B are independent events, the probability that both A and B will occur is just multiplying the probabilities, right? So probability of A times probability of B. So we can extend this to any number of independent events. So let's do a couple of examples of this, okay? A random number generator selects 3 integers from 1 to 20. What is the probability that all 3 numbers are less than or equal to 5? Okay, so A is going to be the event of selecting a number from 1 to 5. So what is the probability of selecting a number from 1 to 5? Well, how many of them are favorable? Well, there's 5 numbers, so 5. And remember, we're picking from 20 numbers. So that's 5 out of 20. Always reduce, we get 1/4. So what if we're going to pick 3 numbers? Okay, and picking one doesn't affect picking the next one, right? So the probability of picking 3 numbers that are less than or equal to 5, they each have a probability of 1/4. So we multiply all of them. 1/4 times 1/4 times 1/4, multiply 1 out of 64. So again, this is the probability of independent events. You take the probability of one of them and you multiply times the probability of the next ones as well. Okay, a few more examples here. ATM PIN codes. So ATM PIN codes usually have 4-digit sequences of numbers. So let's find the probability that if you forget your PIN, you can guess the correct sequence. A at random, and B if you do remember the first 2 digits. So here's your PIN, 4 numbers, right? And you forgot them all. Well, what's the probability that you're going to get the PIN correct? Well, each number is independent. It's not like, oh, if you pick a 9, you can't pick it again. So we're going to look at the probability that you can pick one of these numbers correct, right? So we have 10 choices because you can pick the numbers 1 through 9 plus 0, so that's 10. So what is the probability that you're going to get the first digit correct? Well, 1 out of 10 because one of those numbers is correct out of the total of 10. However, you're doing this 4 times, right? So the probability of guessing each of the digits is 1 out of 10. So you need all 4 digits correct, so that's why we would multiply. So the probability of you getting the first number right, next number, we multiply. So that is a 1 out of 10,000 chance that you will guess your PIN correctly if you forgot them all and you're just randomly typing in the 4 digits, right? But the second example B says, well, what if you recall the first 2 digits? So here's your 4-digit PIN, but you remember the first 2. So then the probability is you just need to guess the second 2 digits correctly, right? Well, the probability of you getting the third digit and the fourth digit is 1 out of 10 for each one. So we multiply. 1 times 1 is 1 over 10 times 10, which is 100. So you have a 1 out of 100 chance, a lot less, which is a lot better chance, right, that you will get this one correct. Less options on the bottom out of 100, 1 out of 100 chance. Okay. So these are all examples of the probability. So just remember, it's pretty much part over whole, your favorable part, or the number of likely or outcomes in your event over total number of possible outcomes there are for that one. Okay. And then that concludes this one. If there are any questions, you can always reach out to tutoring or your instructors. And hopefully you can use all of these as examples as you complete your work for the course.
Thank you, Ms. Camarillo. Thank you for everyone for joining us today. We hope you have a wonderful weekend.
Thank you.